This is Computer Programming 1 from the University of Washington. I'm Martin Dickey, and I'm happy to welcome you back to this lecture in our course. It's a lecture that I've been looking forward to, and the subject is searching, linear and binary search. Like many of our lectures in this half of the course, it will be free of new syntax. Instead, we'll take concepts we already know and apply them to solving some interesting problems. Today we'll talk about what it means to search an array and look at two different algorithms, one called linear search and one called binary search. And then we'll compare the performance of these two algorithms. I think you're going to see that the difference in performance is quite dramatic and certainly unexpected. The problem is to find something. Now, unlike a search and rescue mission, where we don't know exactly where to search, we're going to constrain our emphasis to searching something we can describe, namely an array. This is a very, very common part of many computer programs. We'll state this as follows: determine whether or not a particular value is in the array. If you think about this problem, you might already be able to construct your own solution. We'll see that there is more than one possible way to solve this problem. Let's try to be a little more precise about what the problem is. Specifically, let's take B to be the array we're searching, and N to be the size of the array. And finally, X will be the value we're looking for. Sometimes we call X the target. Now, what do we want this operation to do for us? Well, we want it to tell us whether or not the value is found in the array. You could imagine a couple of ways that this could be done, that this result could be reported. Let's do it this way. If the target X is in the array, I will return its index. That is, the index of the position in the array where X occurs, the position where B sub X is equal to X. Now, what if the value is not in the array? That might be the case as well. In that case, I'll return a -1. This will always be completely clear and unambiguous to the person asking for the search to be done, because -1 is not a valid array index in C. So -1 means failure, and something greater than -1 would mean success. Once we have written a solution, we want to be able to use it perhaps in many places, perhaps in many programs. So the right way to package it is as a function. What does a function like this need to know to do its job? Well, it needs to know what the array is. That might vary from one case to another. It needs to know how large the array is as well. That could also vary. And finally, it has to know what the target is. So it seems like this should be a function of 3 variables. What about the return type? Well, we've decided that the function will either return a -1 or the index. In either of those two cases, the value is an integer. So it seems like the return type ought to be integer. And that would give us the function outline we see here. So far, we've got the outline for a function. We've got its prototype. But we haven't talked yet about the procedure or the algorithm we're going to follow to solve the problem. Let's start with this algorithm. We'll take the array, and we'll begin by looking at the beginning of the array, and we'll examine each element in turn. Now, we only have to do this until we find the target. If we find the target, we can stop and return its index. If the target is not in the array, then we will go all the way through the array. We'll come off the other end. We'll have looked at all the elements, gone past its upper bound, and that will tell us we didn't find the value. Okay. Here's what the code might look like. It's quite straightforward. The main condition is to test one position in the array and see whether or not the value sought is there. In our program, this is one of the conditions on the while loop. So find the while loop in this program. You see it's a compound condition. The first one is almost a technicality. We have to make sure that the index is within the range. We want the search to stop if the index goes out of range. The second part of it is the actual comparison to see whether or not the value we sought has been found. B sub index not equals x. It's not equals because this is a condition for continuing rather than for stopping. So what do we do in the loop if we continue? Continuation means we haven't found the value yet. We want to move to the next position in the loop, in the array. And so the right thing to do is to increment or add 1 to the index. So the loop will execute as long as we haven't found the target or until we've looked everywhere and haven't found it. Which case is it? This is something you can check after leaving the loop with one final condition. If after leaving the loop the index is still less than n, that means we stopped before examining all the entries. That means we must have found what we were looking for. So in that case, we will return index, which was the latest value we used for comparison. Otherwise, we return -1. To help convince ourselves that this works, let's trace an example. The best way to do this is to have the code right next to you. When we start, we'll have to initialize the counter index to the first position in the array. Look at what the call is. The call has 3 parameters. The first one is the array. The second is the size of the array. And the third one is the value being looked for. Is there a mistake here? The call says V, but the example says B. Why the mismatch? Well, the array, the actual array, is declared in the calling function, and it's named V there. But within the function search itself, the local name is B. So this is perfectly all right. So the arrow points to the first position because that's where index is initialized. If you're following along in the program, you'll see that the condition on the while is true at this point. The index is less than n, 8, and the value at this position, 3, is not equal to the one we're looking for, 6. What do we do in this case? We continue. Execute the loop body, add 1 to index, and now we're pointing at position 1. We're still within bounds, and we still haven't found a 6, so we'll continue. We're still in bounds. We still haven't found a 6. We continue. We're still in bounds, and we found what we're looking for. The 6 is there. This will mean the loop condition is false. We'll come out of that loop. We'll execute the final conditional. That checks the index against the bounds, and because it is less than, it tells us that the search was successful. Now, what is the value returned? It's not 6. 6 was an input parameter. The value returned will be the index of the position where the 6 was located. And if you count over from the left, that's position 0, 1, 2, and 3. So the answer that comes back will be a 3. Let's do another couple of these. Same array, same length, different target, 15. Well, you can quickly scan ahead and see what's going to happen. We aren't going to find the 15, but the computer is constrained to follow your algorithm, so it will begin by initializing index, making the test, moving forward. We'll keep doing this. Both conditions on the while keep being true. We're going to get to the last position in the array. Condition is still true, that is, we don't have a match yet. Index gets index plus 1. And now The while condition is false. It's no longer true that the index is less than the size. In fact, it's equal to the size. They're both 8. So we'll leave the while loop, and this time the value returned will be a -1, indicating the search was unsuccessful. If any of this seems mysterious, then you want to go back later, study the program, and follow these traces again. In fact, make up your own examples and trace them too. That will help. There's an interesting technicality about the way a while loop condition is written. It's an AND. We know that by the truth table for AND, both of the conditions have to be true. True and true is true, the only case under which it is true. Otherwise, we have a false condition. Now, simply looking at the truth table, it shouldn't matter which order we check those two conditions. However, in the C programming, it is important. So my first condition, index less than n, will be checked first before I check b sub index not equals x. Can you see why that's important? It's not a fact about conditionals that requires this. It's a fact about arrays. The fact that arrays have bounds and that we don't want to reference outside the bounds. Here's what could happen. If I've searched the whole array, as I had to in this example, and I get to the end, and my index is now equal to the size, and I take the first condition, I postpone the first condition and do the second one, b sub index, I've now just referenced outside the bounds of that array. And that leads to unpredictable results. We don't know what's there. It's garbage. It's an illegal thing to do, logically. Syntactically, it's not. And so the program could have unspecified behavior. That's why the conditions are written in this order. By the way C evaluates compound expressions, it won't do all of the expressions in a compound if it can figure out the true or false value by just looking at the first one. Now in this case, if index is not less than n, in other words, we have a false on that first part, then the AND cannot be true. And so C will not go ahead and try to evaluate the b sub index at all. And that's the behavior that we want to have happen. This algorithm works. It's very straightforward, easy to understand, and easy to program. There's another algorithm that can also be used to search arrays. And that's what we're going to spend time on now. It's called binary search. It only works if the array is sorted. That is, all the elements are in their proper order already. Assuming that the array is sorted, here's the algorithm. Instead of starting at the beginning, and this may seem like a surprise, you start in the middle of the array. You go right smack in the middle. And you see if what you have there is what you're looking for. If it is, you're done. If it's not, then you repeat the process, but you only have to repeat the process with the half of the array where the element could be, and you know which half that is because the array elements are in order. Okay? This is the kind of algorithm we could apply in everyday life if we were looking things up in, say, a book where things are in order, like the yellow pages. All of the topics in the yellow pages are in alphabetical order. Let's say I need food. It's late at night. I'm working on my project for programming, and I've got to find pizza listings. Okay? Let's do binary search on the phone book to find the pizza parlor. Well, the algorithm says, don't start at the first page. That would be linear search. Linear search would say, is pizza on the first page? No. Is it on the second page? No. Is it on the third page? No. It's going to take a while to get to pizza in this phone book. I've got something like 1,745 pages. It's going to take a while to get to the pizza. If we use binary search on it, I go right to the middle. I'm not peeking inside, let me tell you that. I'm not looking at what the subject is. I'm going to go as close to the middle as I can get. It looks like page 963. And then I peek at what the value on that one page is. Now, I look at it. It's Lighting. What about lighting in pizza? Which half of the phone book is it going to be in? It's going to be in this half, right? So I don't need the first part of the phone book at all. I should be able to throw it away and just continue with the second half of the phone book. Let's try it. Let's see if this really works. So now I've got pages 963 to 1757 or whatever it was. And without peeking, I'm going to go right to the middle. And I'm on page 1411, and it's roofing. Okay, how about roofing versus pizza? Seems like I'm going to need just the left-hand side, right? So I tear it up, throw away half, and now my phone book's getting really small fast. Let's do this one more time, or as many times as we need, actually. Maybe somebody out there is counting to see how many times it takes. I open it up, and I've got physicians. Now let me see. H-I. Okay, so pizza, if it's in this book, must be on this side, right? Okay. Let's forget about that. Hope we won't need it again because I can't reach it from here. And now we've just got pages 1187 till the end. I go right to the middle, page 1310. Got produce. Okay. Let's throw away the right-hand side. And now, go to the middle of that. I've got physicians. Okay. Once more, is anybody out there keeping count? We've got, as close to the middle as I can, plumbing. So throw away the right-hand side. I've got plastics. Is it really going to be in this book? Go to the middle here. And what do you know? It's an ad for Pagliacci's. Okay, if anybody was counting out there, I think you'll agree that it took 8 steps. That is, I had to open the phone book and check what was on 8 pages. If I was using linear search on that phone book, how many pages would it have taken? Well, pizza is on page 1258. That's a big difference. 1258 versus 8. Okay, quite a big difference. Okay, that's binary search. Now, that's the big idea. But to program it, we're going to have to be very careful that we get all the details right, because there isn't exactly a programming equivalent of the tear the phone book in half and throw it away statement. So let's go on and see how we do this in the programming. One thing that often helps is to draw a picture of the array as we want it to be when we're finished. And here's a picture I'm going to propose. Now, this way of thinking is new in the course. I haven't done anything exactly like this before. When I'm all finished, what I want to have is the whole phone book or the whole array split right at the point where the target value should be, if it's there. Okay? Remember, X is my target. So if I find that split point, it's going to have the characteristic that everything on the left is less than or equal to it. Everything on the right is greater than. That's the way I'm going to express my explanation of this algorithm and trying to find that split point. Now, I'm going to use the symbol L as the index of the upper part of this blue box. R is right next to it. So R is L plus 1. R is the lowest index of the region where X is greater than 0. Okay, this is an important picture to keep in mind. If you get lost later on in the programming or the explanation of the trace, start by coming back to this picture and see if it makes sense. Now, that's what we want when we're done. But while we're searching, we'll have a different situation. We'll have a blue region of parts of the phone book we know are less than pizza. We'll have the pink region of parts that we're sure are greater than, but there's going to be some parts in the middle, the unprocessed part of the phone book. We don't know about that yet. We know the split point is in there somewhere, but we don't know where. Okay? Now, the key to constructing the algorithm is this. How can we make that green part smaller? Okay? And we're going to make it smaller by having some of it join one of the two sides. Okay? Now in binary search, the way we make this smaller is by going right to the middle of that green area and then comparing that to the target. Okay. We compare that to the target, that'll tell us either that everything on the left of that split point can join the blue region or everything on the right can join the pink region. And we will just have made the green region smaller. Now the beauty of this scheme is that we are going to make the green region smaller every time, in fact by quite a bit, by half. So it's rapidly going to get smaller and smaller until it's vanished and we'll have the picture on the top, which is no green region at all. Okay. Now here I've expressed the same thing but with a little more formality. This is also a good slide to come back to if you get lost in the details later on. For example, it tells us whether the picture is labeled correctly. Is the L in the right place? Should it be just to the left of the line or should it be just to the right? Well, we see that the values in the range 0 to L are supposed to be less than or equal to X. This tells us that L belongs in the blue region and not in the green region. Okay. So just to repeat, blue region, things that are known to be less than or equal to X. Pink region, things that are known to be greater than X. Green region, we don't know yet. Okay. Given that, let's try to construct the code. And let's use a strategy we've recommended before of working from the inside out. We know there's a loop involved. We know that from the description of the algorithm. Let's develop the body of the loop first. Then let's see about the condition. Following that, we can set up the initial conditions, the initializations, and then figure out what the final statement would be when the loop is finished, if all of this works. Okay, so we basically said what the body or the main idea of the while loop is. We just have to express it in C code. The idea is that we go into the middle of the unknown region. Well, just look at the picture and think of the geometry. Where is the middle of that region? It's the average value of L and R, or L plus R over 2. Okay. Since that's integer arithmetic, everything's fine. We won't have fractional values. What do we do at that point? We compare our target to the value that happens to be stored at mid. Okay. Now, here's the key operation. If the value at that point is less than the midpoint, that means everything to the left of that midpoint should join the blue region. And we now have a new value for L. We're going to move L over to the right, expand the blue region. Otherwise, we know that it's the pink region that gets expanded, and we do that by moving R downward to the left, to the midpoint. Okay. All right. This is really the key observation to make. Now, if you accept this, we can go back and fill in the rest of these pieces. Let's consider the condition next. When do we stay in the while loop? Okay. Your first instinct might be, well, we should stay in it as long as the position I'm looking for is not looking at is not the target. Well, you can make that work, but it's actually better to go all the way back to the original picture we had, which showed the pink and blue regions with no green region. So, looking at that picture, the right condition is that L and R are right next to each other. Okay, that R is equal to L plus 1. That's the condition that says we're stopping. Anything other than that is the condition that we continue. So as long as L plus 1 is not R, the two aren't next to each other, we're going to continue this process of whittling down the green area. Okay. Now, each of these steps involves a non-trivial amount of thinking. If this seems more complicated and intricate than any algorithm we've viewed so far in this course, you're exactly right. You're exactly right. Let's continue. We've identified some variables, L, R, and mid. Now, what about their initializations? Well, we don't have to do anything to mid because it gets set to a value each time inside the loop. But L and R have to be carefully set up the first time to make this work. What should they be? Going back to our original concept of the shrinking green region will give us the answer right away. When we start, what is the green region? It's everything. Everything is in the green region. And how do we say that in terms of L and R? Because L and R are not in that region, they're just outside it. Okay? Well, what's just outside the green region on the left is not position 0, but -1. And just outside that region on the right is n, the size of the array. The last index, the bound, is n minus 1, but just past that is n. So we need to do this initialization. Okay, this would be quite mysterious if you were trying to write the program one line at a time from top to bottom. But it's not mysterious if you do it inside out and you keep referring back to the basic pictures that express your goals. Okay, we got the initialization, we got the loop. Now, what do we do when we get out of the loop? It's at this point that we have to return something to the caller. What do we return? Well, either the index where the element is or a -1. Now, look carefully at the picture once we have the split point with L and R next to each other. If the value x is in the array, where must it be? There's only one place it can be. It has to be at L. Okay? Because that whole region are things less than or equal to x, and the array is sorted. So if the value is anywhere in the array, it has to be right at position L. If it's not there, it's not in the array, and that's why we have this picture. Okay? So if the value is at L, you return L, otherwise return -1. What about that other condition? Well, that's the case where we have to check the array index before using it to make sure we're not indexing past one end or other of the array. We'll see examples of that coming up. In fact, now would be a good time to look at a couple of examples. Let's do a search of an array of size 8 to see if the value 3 is there. And of course, as humans, we can scan quickly and see that the 3 is there. So we hope that this is going to return an answer of yes. Technically, it will return a 2 because that's where the value is stored, the value of 3. Okay, let's initialize our L and R pointers. You see where they are. They're bracketing the green region, which is the whole array. -1 and n are their values. Now, we'll check the condition. It's true the first time. L is not next to R. They're widely separated. We'll compute the midpoint. Let's do that together a couple times, and then I'll stop doing it. You'll get the feel for it. It's the average of L and R. So L is -1. R is 8. 8 plus -1 is 7. 7 over 2 is 3. Remember, this is integer division. So we go to position 3 of the array as our midpoint. Is there a 3 there? Remember, this is position 3, but the contents of that array element is 6. So the answer is no, it's not. Well, what is the relationship of our target to that position value? Mid sub x is 6. Is that less than or equal to x? No. It's greater than. And that means that the value, if it occurs, must be on the left-hand side of mid. Okay? So that means we don't have to search any longer on the right-hand side. And so we can make R our upper bound for searching. Okay? So we've now shrunk the part of the array within which we need to search. Okay. Now going back to our original picture, what we've done is we've expanded the known pink part on the right. Now we don't have any pink on this slide, but you can imagine that that's there. We're now restricting our problem to the first part of the phone book, you might say, those values between L and R. Okay. Let's do another step on this. The midpoint next time will be, let's see, -1 plus 3 is 2. 2 over 2 is 1, and so the mid-index is 1. The value stored there is minus 5. Now that is less than x. So we're going to expand the left-hand region. We're going to move L up to the mid value, and now we have this region to search. Notice that L and R are rapidly getting close to one another, but they're not adjacent yet. So I'll do another iteration. The midpoint now is position 2, and that's interesting. That's the value I was looking for. But in terms of this program, I don't stop right there. I have to complete what I'm doing inside the loop. Is the value of 3 less than or equal to 3? Yes, it is. And so that means move up L. Okay. Now, you go back and check the loop condition. Finally, it's true. L and R are right next to each other. Okay. That means the loop terminates. And I'm ready to do my final comparison for L equal to the, or B sub L equal to the value sought. It's true, and so I'll return the index involved, which is 2. And that will tell the caller not only that I found the value, but where it is. Okay. That's a key example. You should be able to trace this in detail just as I did. Okay. If you can't, just take some time, study the program, and go back and try to do it on your own. Let's do a couple more traces, but I promise we won't do them in as excruciating detail as this one. Here we're looking for a value of 17 in the same array. It's not going to be found. You can see that at a glance. Let's see what happens with the algorithm. We start with the whole array needing to be searched. That's how L and R are set. We go to the middle. The value is not there. 6 is less than 17. So I'll be searching the upper half of the array next. I go to the middle of that. Let's see. 21 is greater than 17. So I'll be searching to the left. The midpoint there is 12. 12 is less than 17. So now I'll be searching this region, except, oops, L and R are adjacent. So my loop condition is false. I come out of the loop and I ask the question, is B sub L equal to what I'm looking for, 17? The answer is no. And so this time, the return value from the function is minus 1, meaning I didn't find what I was looking for. When you write programs, coming up with good test cases for them can be very helpful in determining whether the program is correct. Now, you might be tempted just to try 1 or 2 simple cases like we've done and see if they work, but you really ought to think of as many cases you can that might be different in some way. One case that is different would be that if the value sought for is larger than any currently in the array, does the program work in that case? Okay, that is a little different situation. The final picture of L and R will be a little different. Let's rapidly skim through the trace. Going to the midpoint, that's less than 143. So we're going to keep going to the left. Sorry, to the right. 21 is less than our target. Continue to the right. 45 is less than the target. Continue. The new midpoint has a 142, which is less than the target. And now the loop condition is false. L is next to R. And we make the final test. Is 142 equal? No, it's not. Return a minus 1. So we got the right answer in this case. Similarly, you might look at the case where you have a minus 143 as the target. And if you step through this in the same careful way, you'll find yourself always searching the left side of the array, and eventually you'll get down to this picture. Okay. Now, here's a case where the final condition won't check the value stored at position L. Remember, we had a compound condition there, and the first part of that was, is L in range? Okay. And at least it should be programmed that way, so that the comparison here is for the range of L before any use is made of the index. Does the program actually do that? You might want to go back and double check, and if it's not right, then maybe you can fix it up. Is it worth the trouble? This algorithm is considerably more complicated than linear search. And if you are coding it on your own without reference to a previous solution, you can see that it might be quite easy to make a small mistake that could lead to errors. But I think it is worth it just from the pizza example. Let's do this again with some other numbers. Suppose we had 1,000 elements to search. If we do a linear search, we don't know exactly where that value is, but maybe on the average we'd have to look at about half of them starting from the beginning. So maybe take 500 steps or comparisons. On the other hand, in binary search, because we're throwing away half every time, after the first search we have only 500 elements left to consider. After the second step we have only 250. We throw away half of those and we 125, 63. This gets rapidly down to 1. We count those steps, 500, let's see, 1, 2, 3, 4, 5, 6, 7, 8, about 9. Maybe at most 10 steps you're done. That's a big difference. Okay? And as the number of elements gets larger, this difference gets more and more dramatic. What if you had 1,000,000 elements? What do you think it would take? Okay. Well, 1,000,000 is 1,000 times 1,000, so maybe if it took 8, or maybe if it took 10 steps for 1,000, do you think it might take 1,000 times that? That's not really the way to look at it. Here is another way to look at it. How big an array I could search if I am only allowed to examine a certain number of array elements. You could make a table to do this if you don't have a formula. So if I can only make one comparison, I can only search an array of size 1. Okay. Because I'm throwing away half the table each size, by the time I get up to 5 comparisons, I can search an array of size 16. And every time I add one more comparison, I double the size of the array that I can search. So I get up to 1,000,000 pretty fast. Only 21 comparisons can search a table or a phone book of 1,000,000 pages. That to me is still amazing. We can express this in a mathematical formula in a couple of ways. We could say that the size of the array you could search varies with the number of comparisons this way. N is about 2 to the k. K is the number of comparisons. Or you could solve for k in this equation, and you get that k is about equal to the log of n base 2. Now, in linear search, k and n are about the same, or they're roughly the same. Maybe k is half of n or something. Okay. There's a huge difference between the log of a number and the number itself. A little homework problem for tonight might be to just refresh your memory of this. Graph those two functions, log of n and n. And you'll see quite a striking difference in the shape of those two curves. All of this that I've done informally and estimated and showed you with examples can be studied very precisely and has been studied precisely by computer scientists and can be proved in the mathematical sense under very specific and mathematical conditions. What we've seen today is a demonstration of how two different algorithms can have two very different results for the same problem. The binary search is vastly more efficient. Remember, though, that to use binary search, the pages or the numbers have to be in order. My phone book searching would not work if the businesses were not grouped by type and arranged in alphabetical order. If they were simply in there in random order, I'd have no alternative except to go through page by page. Programmers worry about efficiency because they want programs to run fast. Machine resources are limited. People's time and patience is limited. However, just learning more and more details about C and becoming a wizard and mastering the language and the programming environment will not lead you to real efficiencies of this sort in programming. To do that, you have to study real computer science and step back and look at the algorithms involved, which happen to be completely independent of the programming language you are used. In future courses, you might even take this a step further and show mathematically that what you suspect or what you propose is true. All of that is part of computer science. Please join me in future lectures as we continue to explore topics like these.